In section 5.8, we are solving equations by factoring and problem solving. So the reason why we had you learn factoring is so that you can solve polynomial equations, which in turn helps us solve problems that can be modeled by polynomial equations. Now, a polynomial equation is the result of setting two polynomials equal to each other. A polynomial equation is in standard form if one side of the equation is 0. The degree of a simplified polynomial equation in standard form is the same as the highest degree of any of its terms. A polynomial equation of degree 2 is also called a quadratic equation. The method presented in this section for solving polynomial equations is called the factoring method. This method is based on the zero factor property. The zero factor property states that if a and b are real numbers and a times b is equal to 0, then a equals 0 or b equals 0. In math, we use an inclusive or. So when we say or, this could say it could be a equals 0 or b equals 0 or both. So what this property says is that if one of my terms is 0, when I multiply, I end up with 0. That's the only way we can get to 0 with multiplication. One of our terms has to be 0. This property is true for 3 or more factors as well. So to solve polynomial equations by factoring, we write the equation in standard form so that one side of the equation is 0. Factor the polynomial completely. You will set each factor containing a variable equal to 0, solve the resulting equations, and then check each solution in the original equation. So let's look at example number 1. 2x squared plus 9x minus 5 equals 0. So the first thing is it's set equal to 0, which means we can now use that zero factor property. Looking at the left-hand side, we want to factor this. First thing is to look for a GCF, which we don't have one. So we can go ahead and skip to using the Berry method. Our A is 2, our B is 9, and our C is negative 5. So A times C is 2 times negative 5, which is negative 10. So I have to have one positive and one negative. My two factors are 1 and 10, and 2 and 5. Since our B is positive 9, that means that the bigger factor is positive and the smaller factor is negative. And so negative 1 plus 10 would give me the positive 9 I'm looking for. So we bring down the leading coefficient and we split the x's. And then we fill in the remaining pieces with negative 1 and positive 10. The last step of the Berry method is to divide out whatever they have in common. So the first one is 1 and the second one is 2. So we end up with 2x minus 1 and x plus 5 equals 0. This is the same thing we've been doing so far. Now the new part comes in. Once we've factored, we want to set each piece that has a variable in it equal to the 0. So that means I have 2x minus 1 equals 0, and I have x plus 5 equals 0. Now we just want to solve for x. So in this first one, I'm going to add 1 to both sides. So that they cancel on the left, and we get 2x equals 1. And we can divide both sides by 2. So we get x equals 1/2. That's one of our solutions. And then we want to use the other equation and solve for x. So we are going to subtract 5 from both sides. So we end up getting x equals -5. So our two answers are -5 and 1/2. You can also see these written in a set of curly braces. So you might see 1/2 comma -5 inside curly braces. Let's look at example number 2. X times 2x minus 7 equals 4. So there's some issues with this. First thing is that it's not set equal to 0. But before I move that 4, I need to distribute this x to both pieces. So we end up with 2x squared minus 7x equals 4. In order to use the zero factor property, this has to be set equal to 0, which means I am going to subtract 4 from both sides, so that my right-hand side becomes 0. So I have 2x squared minus 7x minus 4 equals 0, and then we want to factor. So do we have a GCF that we can take out? No, because 7 is prime. So A is 2, B is -7, and C is -4. So A times C is 2 times -4, which is -8. We have 1 plus and 1 minus. The two factors of 8 are 1 and 8, and 2 and 4. The goal is to get to -7, which means that my bigger number needs to be negative and my smaller number is going to be positive. So positive 1 minus 8 will give me the -7 I'm looking for. We bring down the leading coefficient and we split the x's, and then we fill in the remaining pieces. And the last step is to divide out whatever they have in common. So in the first one, it's just a 1. In the second one, it's a 2. So we get 2x plus 1, and we get x minus 4 equals 0. Now that I have factored the left-hand side completely, we want to set both of our binomials equal to 0. So we have 2x plus 1 equals 0, and we have x minus 4 equals 0. Well, the second one is pretty easy to solve. We're just going to add 4 to both sides. And we end up with x equals 4. And then for the other one, solving for x, we're going to subtract 1 from both sides. We get 2x equals -1. And then dividing both sides by 2. We get x equals -1/2. So x equals -1/2 and x equals 4 are solutions to our original equation. And again, you can see these in a set of curly braces as another way to write the answer. To apply the zero factor property, one side has to be 0. So we can't just set each factor equal to 4. We had to move the 4 over in order to utilize that property, which is why it's the zero factor property. Let's look at example number 3. We've got x cubed equals 4x. So the problem again is that one side is not equal to 0. So we need to move the 4x to the other side. So we are going to subtract 4x from both sides. So we get x cubed minus 4x equals 0. The first thing we always look for is a GCF, which this one does have one. The GCF is just x. So when I pull out x, what I have left is x squared minus 4 equals 0. But you should notice that x squared minus 4 is a difference of 2 squares, which means that I can break this down even further. We have our x out front, and x squared minus 4 is going to turn into x plus 2, x minus 2. Again, you could use the Berry method on that piece, or you can just notice that it's a difference of 2 squares. And so now we're going to set all 3 of these pieces equal to 0. We have just our x up front equals 0. We have x plus 2 equals 0. And we have x minus 2 equals 0. The first one's already done. We can't really simplify that anymore. But we can simplify the other two. We can subtract 2 on the first one, and we can add 2 on the second one. And so it ends up canceling on the left-hand side, and we get that x equals negative 2, and we also get that x equals 2. So this time we got 3 solutions. X equals 2, x equals negative 2, and x equals 0. Now notice that the third degree equation in that last example gave me 3 solutions. If we go back and look at the previous ones, the degree was 2 and we got 2 solutions. Let's try example number 4. We have x cubed plus 5x squared equals x plus 5. So again, we don't have one side equal to 0, which means we need to move everything to one side. So I'm going to subtract x and I'm going to subtract 5 from both sides. So on the right, the x's cancel and the 5's cancel. And on the left, we now have x cubed plus 5x squared minus x minus 5 equals 0. If we have 4 terms, the method for factoring is factoring by grouping, which is where we split the polynomial down the middle. Looking at the first 2 terms, x cubed plus 5x squared, they both have an x squared in common, and we have an x plus 5 left over. Now remember, we have to copy and paste the x plus 5 to the other side for this to work. And we need to figure out what goes in front so that when I distribute, we end up with negative x minus 5. So we would need to put a negative 1 up front, so we would end up with negative x minus 5. So what these two pieces have in common is x plus 5, and what's left over is x squared minus 1. But again, you should notice that x squared minus 1 is a difference of two squares. And so we can actually write this as x plus 5 times x plus 1 times x minus 1. And so again, now we're going to set all three pieces equal to 0. X plus 5 equals 0. X plus 1 equals 0. And x minus 1 equals 0. So in the first one, we can subtract 5 from both sides. In the second one, we're going to subtract 1 from both sides. And in the third one, we're going to add 1 to both sides. You can do these all one at a time and then move to the next one, or you can try and do them simultaneously. So we end up with x equals negative 5 as a solution, x equals negative 1 as a solution, and x equals 1 as the third solution. Again, this was a third degree polynomial and we got 3 answers. You could also see it written in the curly braces, negative 5, negative 1, and 1. Solving problems modeled by polynomial equations. So this just means we're going to look at word problems and then use factoring to solve them. One thing you want to keep in mind is that a person's weight or the length of a side of a geometric figure is always a positive number. So you'll discard solutions that do not make sense as solutions of the problem. Some of the exercises at the end of this section use the Pythagorean theorem. So a right triangle is a triangle that contains a 90-degree angle or a right angle. The hypotenuse of a right triangle is the side opposite of the right angle, and it is the longest side of the triangle. The legs of a right triangle are the other two sides of the triangle. So the legs we label as A or B, it doesn't matter which one, but the hypotenuse is always C. And so we can use the fact that A squared plus B squared is equal to C squared. So while framing an addition to an existing home, a carpenter used the Pythagorean theorem to determine whether a wall was square. That is, whether the wall formed a right angle with the floor. He used a triangle whose sides are 3 consecutive integers. Find a right triangle whose sides are 3 consecutive integers. So what does 3 consecutive integers even mean? Well, consecutive just means that they're in a row. So 1, 2, 3 would be 3 consecutive integers. 4, 5, 6 would be another example of 3 consecutive integers. So it's just 3 numbers in a row. Let's go ahead and draw a picture to help us solve this. We know that we're using a right triangle. And we don't know any of the sides, but we know that they are 3 consecutive integers. So if we let the first one be x, the next side would be x plus 1, and the third side, which would be the longest, is x plus 2. You can check that this makes sense because if we plug in any number for x, let's say 3, The next one would be 3 plus 1, which is 4. And then 3 plus 2, which is 5. So you got 3, 4, 5, or 3 consecutive integers. You could plug in 10. You would get 10, 11, 12. So now that it's set up correctly, we can use the Pythagorean theorem to solve this equation. So we're going to let this first one be A. The second one is going to be B. And the hypotenuse is C. So using our formula, a squared plus b squared equals c squared, we get x squared plus x plus 1 squared equals x plus 2 squared. We want to simplify this as much as possible. So I'm going to multiply x plus 1 times x plus 1, because that's what x plus 1 squared is. And I'm going to do the same thing on the right, except I'm doing x plus 2 times x plus 2. So we're just foiling. We get x squared plus x plus 1. And on the right hand side we get x squared plus 2x plus 2x plus 4. So let's go ahead and combine like terms. We have x squared and x squared. We have x and x. And on the right hand side we have 2x and 2x. And so we end up with 2x squared plus 2x plus 1 equals x squared plus 4x plus 4. We need to set this equal to 0. So I'm going to subtract x squared, subtract 4x, and subtract 4 from both sides. And so on the right hand side, everything is going to cancel. And on the left, I end up with x squared minus 2x minus 3 equals 0. Now we know how to solve this. We can just use the Berry method to factor. We don't have a GCF we have to worry about. So a is 1, b is negative 2, and c is negative 3. A times c is 1 times negative 3, which gives me negative 3. I have to have one positive and one negative, and the only factor of 3 is 1 and 3. We need to have a negative 2, which means that the bigger number is negative and the smaller number is positive. And so plus 1 minus 3 gives me negative 2. So we bring down the leading coefficient, we split our x's. We have x plus 1, and we have x minus 3 equals 0. We would divide out whatever they have in common, but the only thing they have in common is a 1. And so I end up with x plus 1 times x minus 3 equals 0. And so now what I want to do is I want to set each piece equal to 0 and solve. So x plus 1 equals 0, and x minus 3 equals 0. We subtract 1 from both sides on the first one, and we add 3 on both sides for the second one. So x is equal to negative 1, and x is equal to 3. Now which one can we throw out? Well, remember what x is actually referring to in the diagram. We're referring to the length of a side. So length can never be negative. So we can get rid of x equals -1 as a solution, and we will only be using x equals 3. So since x equals 3, we can figure out the other two sides. X plus 1 would give me 3 plus 1, which is 4. And x plus 2 would give me 3 plus 2, which is 5. So we ended up getting 3, 4, 5. The last thing we're going to talk about in this chapter is finding the x-intercepts of polynomial functions. So recall that to find the x-intercepts of a graph of a function, we let y be equal to 0 and solve for x. So we know that the solutions of the equation x plus 2 times x minus 6 equals 0 are -2 and 6. These solutions give us important information about the related polynomial function p of x equals x plus 2 times x minus 6. We know that when x equals -2 or when x equals 6, the value of p of x is equal to 0. So we know that -2, 0 and 6, 0 are the x-intercepts of the graph of p of x. Hence, if we are given the solutions to a polynomial, we can find the original polynomial. It's essentially like working backwards in a factoring problem. So all we're going to do is we're just going to work backwards from factoring. So I want to write a quadratic equation that has the solutions 1 and -7. So we know that x equals 1, and we know that x equals -7. We want to set both of these equal to 0. So I'm going to subtract 1 from both sides. And we get x minus 1 equals 0. And I'm also going to add 7 to both sides. So we end up with x plus 7 equals 0. So now that we have both of our factors equal to 0, we can smush them together into a multiplication problem. We have x minus 1 times x plus 7 equals 0. And the last step is we just want to FOIL this. So we end up with x squared plus 7x minus x minus 7 equals 0. We can combine like terms. We end up with x squared plus 6x minus 7 equals 0. And so that means we can write this as our function f of x equals x squared plus 6x minus 7. And if you were to then factor this out, you would end up getting that your solutions were 1 and -7.